element changes from one place to another in a XY plane. And in figure B, your the coordinate system is rotated about an angle theta, and thereby the it seems that your the transformation takes place and your points are being changed. So the first case is called active transformation, and the second case is called passive transformation. In active transformation, the rigid body is rotated about an axis by a certain angle. And in passive transformation, the coordinate system is rotated about an axis by a certain angle. Okay, are you getting it? So, it is a continuous group or Lie group. Lie group is popularly known as continuous group. Am I audible?
Yes, sir.
If the screen will not be visible at some point of time, you please intimate me. So continuous group or Lie group are groups such that each element of the group is specified by one or several in finite number of real parameters. Such groups necessarily have an infinite number of elements. The group law is the rule which tells us how to calculate the parameters of the product element given two sets of parameters specifying the two elements. So there are some simplest example of continuous groups as shown in the screen. 3 examples I am showing you. Then your orthogonal group O3. As a simple and important example, let us consider rotation in 3-dimensional space. Rotation have the property that there is one special point which remain fixed, and second is distances between any pair of points of the rotated body remain unchanged. So you can take the fixed point O as the origin of Cartesian coordinates, and let a general point P of the body have the coordinates x1, x2 and x3 before the rotation, and your x1 dash, 2 dash, 3 dash after the rotation. So you can write x1 dash square plus x2 dash square plus x3 dash square is equal to x1 square plus x2 square plus x3 square, and where 1, 2, 3 are in superscript. So you can write it as a matrix equation where x is equal to a matrix comprising of x1, x2 and x3, and x dash comprises of the elements having in a matrix form x1 dash, x2 dash, x3 dash. Then your x dash t x dash is equal to xt x dash, and this transpose relation between the coordinates of x dash and x you can see, and this relation between the coordinate x dash and x is linear. Then you can write x dash is equal to rx, and in the matrix form as shown in the screen. The space inversion or parity matrix which reverses the sign of each coordinates are shown in the screen, and your is is equal to you can write in a matrix form -1 0 0 0 -1 0 and 0 0 -1 is equal to -1 belongs to O3. Then the subgroup SO3 or rotation group. A general element of O3 can have a determinant either +1 or -1. The product of two matrices with a determinant +1 is again a matrix with a determinant +1. Therefore, the subset O3 which has matrices with a determinant +1 is a subgroup denoted by SO3 called the special orthogonal group. Thus, the group O3 has two cosets, the subset SO3 and the set of matrices with a determinant -1. So since the space inversion matrix has a determinant equal to -1, any O3 matrix T with a determinant equal to -1 can be written as T is equal to IS capital R. So you can note that if T belongs to O3, then both T and T inverse has the same determinant because T inverse is equal to T transpose. And your O3 and SO3 are more elaborate example of continuous or Lie groups. And in our case, O3 needs 3 real parameters to specify a group element. A 3x3 matrix R has 9 elements, and the orthogonality condition R transpose R is equal to 1 is equivalent to your 6 conditions, where R transpose T is a symmetric matrix with 6 elements actually independent and 3 elements on a diagonal and 3 elements on one side of the diagonal. Am I audible? Am I audible? कुछ सुनाई दे रहा है? There is
Yes,
some.
yes, sir.
I think the screen is visible.
Sir, you are sharing your screens with everyone.
Okay, okay. So O3 and SO3 are more elaborate example of continuous life as I told you. And elements on one side of the diagonal are equal to corresponding element on the other side in the symmetric matrix. Therefore, there are only 3 parameters. And one parameter subgroup of SO3, you can see rotation about an axis in figure 19.2 in the screen. So a rotation in which not just a single point but a whole line remains fixed is called rotation about an axis, as shown in the figure 19.2. So these are especially simple rotation because if the axis is fixed, a single parameter, the angle of rotation is enough to specify the rotation completely. And it was proved by Euler in the year 1776 that every rotation can be seen as a rotation about an axis by a definite angle. So one parameter group of rotation with a fixed axis is called the group SO2 group, as a rotation in the 2-dimensional plane perpendicular to the axis. So it is a subgroup of SO3. Similarly, you can have your generators of one parameter subgroups. Since rotation about a fixed axis adds up, it is possible to build finite rotation by successive application of a very large number of very small rotations. This suggests that we should look at the structure of infinitesimal rotation. An active rotation by an angle theta about the 3 axes in a right-handed Cartesian coordinate system is the SO3 matrix, as shown in the screen. So R3, which is a function of theta, can be written as a matrix form: cos theta minus sin theta 0, sin theta cos theta 0, 0, 0, 1. And your 1 minus theta square by 2 plus so on and so forth, minus theta plus theta q by 3 factorial plus so on and so forth, 0. Then your theta minus theta q by 3 factorial plus so on and so forth, 1 minus theta square by 2 factorial plus so on and so forth, 0. Then 0, 0, 1. Where your theta greater than 0 means that the rotation is in the right-handed sleeve sense, that is anti-clockwise in the plane parallel to 1, 2 plane. For infinitesimal theta, this matrix is limited to 0. R3, which is a function of theta, is equal to 1 cos theta multiplied by the matrix 0 minus 1, 0, 1, 0, 0, 0, 0, 0, minus theta square by 2 factorial multiplied by the matrix 1, 0, 0, 0, 1, 0, 0, 0, 0, and this can be written as 1 plus theta j3 plus theta square by 2 factorial j3 square, and your j3 matrix will nothing but 0 minus 1, 0, 1, 0, 0, 0, 0, 0 matrix. So you can say that the j3 square is equal to minus 1 and j3q is equal to minus j3, j3 4, j3 to the power 4 is equal to 1. Therefore, even for finite theta. And j3 is called the generator of rotation about the 3 axis because all finite angle rotation about 3 axis can be built out of it. Similarly, an infinitesimal rotation about the 1 axis, that is r1 theta, is equal to in the matrix form 1, 0, 0, 0 cos theta minus sin theta, 0 sin theta cos theta, which can be written in matrix from 1, 0, 0, 0, 1 minus theta square by 2 factorial plus so on and so forth, minus theta plus theta q by 3 factorial so on and so forth, 0, theta minus theta q by 3 factorial plus so on and so forth, 1 minus theta square by 2 factorial so on and so forth, and this can be written as r1, which is a function of theta, is equal to 1 plus theta j1 plus theta 2 by 2 j1 square plus so on and so forth is equal to exponential theta j1, with j1 is equal to 0 0 0 0 0 minus 1 0 1 0 matrix. And an infinitesimal rotation about the two axes will be r2 theta is equal to in matrix form cos theta 0 sin theta 0 1 0 minus sin theta 0 cos theta. And in a similar manner, you can have your r2 with j2 is equal to 0 0 1 0 0 0 minus 1 0 0. And your r2 theta, r2 which is a function theta is equal to exponential theta j2. Then your rotation about axis in different directions do not commute, you know. So the simple is equal to axis 2 theta and phi being small. So you can see how much mismatch is there when these two infinitesimal rotations are applied one after the other in two different ways. So you can write if R1 R2 is equal to R1 R2 minus R2 R1, where 0, then the result of R1 R2 and R2 R1 would have been the same acting on any vector x. So this is the explanation as shown in the screen, and you can find that J2 J1 minus J1 J2 is equal to minus J3. So the resulting rotation axis is the negative 3 axis. We have taken rotations about the coordinate axis, but one could take any arbitrary directions and obtain similar relations between generators. The relation I have shown you now in the screen, that the commutator of the generator of rotations in 1 and 2 direction is the generator in the 3 direction. So your in square bracket J1 J2 is equal to J1 comma J2 minus J2 comma J1 is equal to J3. So you can show that in square bracket J2 J3 is equal to J1, and in square bracket J3 J1 is equal to J2. Then Lie algebra of generators. A general rotation that is a member of SO3 is an orthogonal 3 cross 3 matrix R with a determinant equal to 1. The identity matrix corresponds to no rotation. Therefore, an infinitesimal rotation is a matrix infinitesimally different from the identity matrix. So you can write R is equal to 1 plus capital M, where elements of M are all small quantities. The condition of orthogonality requires that 1 is equal to R transpose multiplied by R is equal to 1 plus M transpose multiplied by 1 plus M. This can be written as 1 plus M transpose plus M plus second order of smallness. So therefore, in the limit of infinitesimal rotation, you can write M transpose plus M is equal to 0 or M transpose is equal to minus M. The infinitesimal rotation matrix differs from the identity matrix by an asymmetric matrix as shown in the screen. So you can have your M is equal to minus Cj1 plus Bj2 minus Aj3, and the derivation is shown in the screen. And you have M is equal to minus Nm, and it is antisymmetric, and it satisfies the Jacobi identity, that is M comma N is equal to M comma N L plus NL M is equal to 0 as shown in the screen. Any vector space which has a bilinear relation defined on it is an algebra. The vector space like the one I have discussed now with an asymmetric bilinear product satisfying Jacobi identity is called a Lie algebra. So a bilinear product here is the commutator of two matrices. Most products encountered in physics are associative products. For example, the matrix multiplication AB multiplied by C is equal to A multiplied by BC. But the Jacobi identity shows that the product in a Lie algebra is non-associative. That is Mn P is equal to M is not equal to Mn in general. The only other place a non-associative product is encountered in elementary physics is the Poisson bracket in classical mechanics. There too, there is a Lie algebra of phase space function. Okay. Then there are different notations. I have shown you in the screen. However, in the generator of all symmetric transformation are proportional to physical quantities or observables, which are represented by Hermitian operator as shown in the screen. And your generator J cap are called components of angular momentum, and you have a detailed idea of those things in your quantity after this course. We have given the generators starting from the active rotation matrix as shown in the screen. Then your Minkowitz is Lorentz group. Two units such as time, such that time is measured in meters. We use units such that time is measured in meters with the help of a universal constant small c, which represents velocity in vacuum. This effectively makes c is equal to 1 in a relativity formula, and velocities become dimensionless numbers. So if you recall Lorentz transformation, then you might have recollect that in matrix form T dash, X dash, Y dash, Z dash is equal to in 1 by minus 1 by root over 1 minus V square minus V by root over 1 0 0 minus V root over 1 minus V square 1 minus root over of 1 by V square 0 0 0 0 1 0 0 0 0 multiplied matrix T x y x T x y z, and it relates the same event P, which is specified by T x y T comma x comma y comma z and T dash comma x comma x dash comma y dash comma z dash respectively in the two frames of reference S and S dash, which means we are using passive transformation. That is, the coordinate system is only changed. The two frames are such that their axes are parallel, the x and x dash are collinear, and your S dash moves with velocity v with respect to s along the x-axis. And the clocks are set so that when the origins of the two frames coincide, your t is equal to 0 is equal to t dash. And this is written as the matrix equation x dash is equal to Lx. When x is the single Coulomb matrix, in matrix form x0, x2, x1, x2, x3, having 0, 1, 2, 3 as a superscript, is equal to in matrix form t, x, y, z. And similarly for x dash, the matrix L is a 4 cross 4 matrix. The example is given, and it is a special Lorentz transformation called boost in the one direction. So a Lorentz transformation is a real 4 cross 4 matrix L, which transforms x into x dash is equal to Lx of that your minus x0 square minus plus x1 square plus x2 square plus x3 square is equal to minus x dash 0 square plus x dash 1 square plus x dash 2 square plus x dash 3 square. And this condition can be written more compactly using the matrix eta is equal to in matrix form, and in diagonal you can place minus 1 1 1 1, and your x transpose eta x is equal to x dash transpose eta x dash. Therefore, if x dash is equal to Lx, then the condition for L to be a Lorentz matrix is x dash t x dash transpose eta x dash is equal to x transpose LT eta Lx is equal to x transpose eta x. So since this is true for an arbitrary x, follows that L transpose eta L is equal to eta. Thus, any real 4 cross 4 matrix that satisfies the above equation is a Lorentz transformation. Okay. So what is Minkowitz space? Am I audible?
Yes, sir.
You can think of a 4-dimensional vector space in analogy to 3-dimensional space where position vector are x is equal to x0, x1, x2 and x3, and where the inner product or the dot product between two vectors x and y is given by x comma y is equal to x dot y is equal to x transpose eta y, and this 4 dimensional space is called the Minkowski space. And here the length square of a vector is shown in the screen. The set of vectors corresponding to x dot x is equal to 0 is called the light-like or null vectors. Null vectors form a double cone, and this is the surface in Minkowski space satisfying x0 square is equal to x1 square plus x2 square plus x3 square, and your x0 is equal to root plus minus root over of x1 square plus x2 square plus x3 square with the vertex at the origin 0, 0, 0, 0 transpose and the vertex angle of 45 degree. This cone is called the light cone. The time axis is the axis of the cone. The positive side of the cone, that is the half cone through which the positive half of the time axis passes, is called the forward light cone, and the negative side of the cone, the backward light cone. All vectors with x comma x smaller than 0 lie within the light cone, and they are called time-like vectors. The remaining vector with x dot x greater than 0 lie in the wedge-like region, and they are called space-like vectors. And let L be the set of 4 cross 4 Lorentz transformator matrices, and from there you can have your Lorentz group. These form a group and is called Lorentz group with matrix multiplication as the group law. The inverse of each matrix exists because determinant of L is not equal to 0, and we know that the determinant of any Lorentz matrix can be either +1 or -1. This follows from L transpose eta L is equal to eta, and taking determinant on both sides to obtain determinant of L square is equal to 1. So you can check L inverse is equal to eta, L transpose eta. And your Lorentz group, special linear group 2 cross 2 complex matrices, and your SL2, C stands for special linear group of 2 cross 2 complex matrices. The only special thing about elements of SL2, C is that their determinant is equal to 1. The fundamental fact about these matrices is that for every A belongs to SL2, C, there is a proper orthochronous Lorentz transformation LA belongs to L subscript plus of such that your LA L2 is equal to L A1 A2. Let us have a set of 2 cross 2 matrix, and so that 2 cross 2 matrix form a 4-dimensional linear vector space, and from those you can have your Pauli matrices, which is very much used in your quantum mechanics. So your sigma 0, the 4 Pauli matrices are sigma 0, sigma 1, sigma 2 and sigma 3, which is a 2 cross 2 Hermitian matrix, and sigma 0 is equal to in matrix from 1 0 0 1, sigma 1 is equal to in matrix from 0 1 1 0, sigma 2 in matrix form is equal to 0 minus I 0, and sigma 3 is in matrix from 1 0 0 minus 1. So any 4 linearly independent Hermitian matrices would have been equally good, but these are the ones traditionally used, and they have the properties as shown in the screen. So your squares of all Pauli matrices are equal to identity, that is sigma 0 square is equal to 1, sigma 1 square is equal to 1, sigma 2 square is equal to 1, and sigma 3 square is equal to 1. And your matrices sigma I is equal to 1, 2, 3 have trace 0. Trace is what? The addition, the summation of the diagonal elements. And sigma 1, sigma 2 is equal to minus sigma 2, sigma 1 is equal to I sigma 3. And other similar relations are obtained by rotating 1, 2, 3 cyclically, 1, 2, 3 cyclically. So these properties imply that a trace of sigma nu is equal to 2 delta mu nu, where delta mu nu is the Kronecker delta equal to 0 when mu is not is equal to nu, and 1 when two indices are the same. Although the placing of the subscripts on the constant Pauli matrix is like that of covariant vector, it is not a covariant 4 vector. We will always use Pauli matrices with a lower index. So you have, I have explained the things as shown in the screen. You can go through it. And you can prove that LA is equal to, LA belongs to L plus dagger. Then your homomorphism SL2 comma C. Uh, uh, so the formula relating to A to LA also shows that the correspondence is a 2:1 mapping with A and minus A giving the same LA belongs to LA plus dagger. But how do we know that there are just two and not more a dash for the given LA? We try to find its kernel, and if LA is equal to 1, the 4 cross 4 unit matrix, then we can have our A. There are some worked out examples you can try, and if any doubt, you can ask me. One of them is using the formula above shows the only possibility that A is equal to 1 or A is equal to minus 1. That is 2 cross 2 unit matrices, and the solution is there in the screen. If you have doubt in any point of time, then you can ask. Then 6 parameters of SL2 comma C, a typical matrix in SL2 comma C is A is equal to matrix from AB, CD, where AD minus BC is equal to 1. And you can say that AD minus BC is equal to 1, where A, B, C, D are complex numbers with one complex condition among them. Then Bush and Hermitian SL2 comma C matrices. So every Hermitian SL2 comma C matrices can be written in the standard form. A is equal to cosine hyperbolic alpha by 2 plus n dot sigma vector sine hyperbolic alpha by 2. Because if A is Hermitian, it can be written as A is equal to summation A superscript mu multiplied by sigma subscript mu with real A mu, and the determinant of A is equal to 1. So such matrices represent a boost in the direction of unit vector A and with velocity given by tan hyperbolic alpha. Now the example is shown in the screen. And if alpha is greater than 0, then this is an active Lorentz boost in the direction of coordinate 3 axis with velocity v is equal to tan hyperbolic alpha. So this boost transformation, the momentum for vector m, 0, 0, 0 of a particular mass m at rest to that of the particle moving along 3 axis with momentum 4 vector. So the speed of particle is b is equal to modulus of p by p 0 is equal to tan hyperbolic alpha. So there is a SAQ, so that if A is Hermitian, then LA is symmetric. So there are some examples as I show in the screen. You can go through this. And a unitary SL2 comma C matrix form a subgroup of SL2 comma C, and they correspond to rotation. And by the example showing in the screen, you can understand it. Please go through it. If you are in doubt, please ask. Then any SL2 comma C matrix can be written as a product of a boost and an SU2 matrix. And please go through the examples as shown in the screen. A very useful and interesting matrix is the SC2 element, that is epsilon is equal to in matrix from 0, 1, minus 1, 0. So the matrix epsilon and other useful formula are shown in the screen. Under parity, inverted Pauli matrix, sigma subscript mu superscript p are defined as shown in the screen. Okay, there are some terminal questions. There are self-assessment questions as shown in the screen. You can go through this, and if you have any doubt, you can ask. Okay. So next we will have your unit I think 2. So unit 2, and if there are some parts left in between our discussion, you can mark those, and we shall discuss those in the next class. So there is matrix algebra and other things which we will discuss in the next class. Am I audible?
Yes, sir.
Okay, okay. So I have forwarded the PDF of the notes to one of your friend who has messaged me yesterday, and you can go through those notes.
Yes, sir.
Thank you.
Thank you, sir.
Thank you.